OK, let's continue with step 2, determining the distribution, or the asymptotic distribution of sigma hat squared. So what's going on is that we just determined the asymptotic distribution of these two ingredients, and now we want to combine them into sigma hat squared and know what the limiting distribution is. This is given to us by the delta method. Because we know that this is a continuously differentiable function of these two components. So the delta method in its general form that you learned in class is the following. Given a sequence of random variables, Tn, such that their centered version, centered by theta, by a random vector theta, and rescaled by square root of n, if this distribution, if this goes to a normal distribution with covariance matrix sigma, and we just calculated the covariance matrix in our particular case, and I have, and here Tn can be a d-dimensional random variable, and this would in turn be a d by d matrix. Then if I have a continuously differentiable function, let's just, for simplicity, assume that it actually goes from Rd to R. And it is continuously differentiable at theta, then I know what the limiting distribution of g of Tn is. Namely, I still scale by square root of n. I look at g of Tn. I subtract off g of theta, so this just propagates through. And then what happens to my variance, my asymptotic variance? This is what I care about. It is going to get scaled with, well, a linear approximation to g, namely the gradient of g at theta, transpose, sigma, and again, gradient of theta. So intuitively, this just means how much does g locally spread out? How sensitive is it with respect to each of the variables? And then I account for the interdependence of all the variables within the covariance matrix sigma. OK, so remember our setup. We set yi to be xi squared, wi to be xi. That means if I consider Tn the joint average of these two random variables, so let's set Tn to be the joint average, the average vector, then I recover my estimator as g of Tn, where g, let's use lowercase letters now, of yw is y minus w squared. So this is a nice continuously differentiable function. So let's calculate its gradient. The gradient is just the partial derivative. So first, we differentiate this with respect to y. It gives us a 1 from this term and 0 from that term, so just 1. And then the second entry is the partial derivative with respect to w. This term will just have 0 partial derivative with respect to w, and this term here is minus 2w. That means, in turn, that we get the asymptotic distribution of our estimator sigma hat squared is the following. We scale by n, square root n, take sigma hat squared, which is just g of Tn, minus the expectation at the limit, which we calculated to be sigma squared. We briefly mentioned that sigma hat squared is consistent. Sorry. So that's what we want to have, but if we just plug it into the delta method, what we need here is the limit of Tn first, which is going to be just the expectation of xi squared and the expectation of xi. But then we apply our same function here, and we regain the variance. So this is going to be correct. And as n goes to infinity, this goes to a centered normal distribution. And now here it comes. Now we have to plug in the gradient of g. So what's the gradient of g? Evaluated at theta. So let's write down theta is just going to be the expectation of y1 and expectation of w1, which is y1 is xi squared. So this is going to be sigma squared. And this is just going to be 0 because we assume that our variables are centered. Great. So we evaluate this gradient at theta. So that means, well, it doesn't actually depend on the first value of theta. So this is just going to be 1. And w is 0. So that's going to be our vector. We transpose it. We write down the covariance matrix we calculated previously. It looked like this. And we hit it with the same vector again. Great. So let's multiply this out. What's happening is that this vector just selects this entry of the matrix. So we end up with 2 times sigma to the 4 as the asymptotic variance of our estimator sigma hat squared. Let's write that down. So once I calculated this, I can safely go back to standardizing this expression first and then having a standard normal. That means, let me write it down as square root n times sigma hat squared minus sigma squared divided by square root 2 sigma squared goes to standard normal. OK. Now, as a problem for you, what happens here if I allow a mean mu here, if it's not centered anymore? And I'm going to erase. And when I'm back, we're trying to tackle point number 3, how to turn this into a confidence interval, into an asymptotic confidence interval.